The reason they can't have that smooth muscle is because at the capillaries, what happens? What's the important part of the capillaries? Let's go Reza. Now that's right, diffusion. Next we move into your venules, right? So the venules after the capillaries. So remember the capillary is just one cell flowing at a time. Venule starts to get a little bit larger. And it has a little bit of smooth muscle along the outside. It has to deal with a little bit more pressure. We'll talk about the pressure, Ricardo, afterwards. Now, can anyone tell me what this represents here? Abdel, yeah. It's a valve, not an AV valve. AV valves are only found in your heart. Yeah. Your veins also have valves. So as your blood is flowing, remember, so these are lined up next to each other. These start to flow. Right? As your heart beats, these valves open and close. Right? So your heart beats, it adds pressure, which opens these valves, and your blood starts flowing from your venules to your capillaries. And then once your heartbeat stops, these valves close. Now there's a reason for this. Okay? But what happens is, so as your heart, remember we have the thick wall cardiac muscle here, right? This pumps, your left ventricle pumps the blood into your aorta, into your body, okay? Because of this muscle and because of the distance that blood has to go, that blood pressure is really high. Blood pressure is huge here and in your arteries, and you'll see this when we work our way back. Once it gets to the veins, right, the blood pressure has decreased because you're now farther away from, you're like about as far away from the heart as you can get, right? So what happens is, the pressure isn't as high to keep this blood flowing smoothly, and say you have a vein that's coming up your foot, right? You have to fight gravity. Your blood has to fight gravity to come back up through your body to get to your heart, right? So these valves, what they do is they open and close, ensuring that there's no way that you can have backflow of blood. So say blood is going through your veins, right, back up to your heart, right, and there's that split second, and I mean split second, where there's not a high enough blood pressure to keep it moving up. These valves are there to make sure that it doesn't flow right back down into your feet. All right, so are we okay with this so far? Does anyone need more time for that now? Okay, so now we're going to flip. We remove our valves. We've gone through our veins, we're back at the heart, we're getting pumped out back through arteries, right? Our arteries have the most smooth muscle surrounding them of any other blood vessel that we have. More than your veins, more than your arterioles, more than your venules. Can anyone take a guess as to why they need the most smooth muscle? Let's go with Ivan.
Is it because that's where the most pressure is, just when you start from the heart?
That's exactly right, yeah. The arteries there's the most pressure is put on the arteries because it's the closest to the heart, remember. So that pressure is going to start out really high, and you need all this smooth muscle to be able to handle that pressure. So as your heart is beating, it's going to be pumping this blood. It's going to flow through into your arterioles. Now the arterioles have more smooth muscle than your venules, okay? And that's because, again, there's more pressure on the arterioles than there are on the venules, okay? And then finally, we get the blood flow back into the capillaries. This all continues moving. And the capillaries are the same on both sides of the capillary bed. The capillaries are the same on both sides, allowing for gas diffusion. Now, why don't arteries have valves? Good questions. Anything else on this? No? All right, cool. We have another representation too, just so you can see cross-sectionally. this is how, when you see arteries in textbooks, you're going to see the cross section more than anything. So when we're looking at a vein, say you look in your textbook, most likely you're going to see it from this view. Right, like here, you're going to see layer of muscle, your endothelium, and your blood in the middle. Did you see that in your textbook when you were making your notes? Any cross sections? So usually you won't see it set up like this. Just so you know, it's going to normally be cross sectional like this. So just going to, then you'll be able to see the layers. All right. The next thing we're going to look at is heartbeat. We're going to be looking at the rhythm of the heart. So, the heart beats, the heart does not require stimulation from your nervous system to beat on a regular basis. All right, you all had it in your notes. It's called, I believe it's myogenic contraction, right? Myogenic contraction of cardiac muscle found in your right atrium. This is called your sinoatrial node, or your SA node for short. That's what's shown by the yellow cells. Okay. Your sinoatrial node is what starts the electrical signal that causes the heart to beat. Sinoatrial node, or this is the SA node.
What does it do?
It starts the electrical signals that causes your heart to beat. Because remember, your heart is a muscle, and like all muscles, it needs a signal to tell it to contract and when to relax. Yes?
Is that a part of the pacemaker? Or
That is your natural pacemaker. Yes. Very good. So the SA node is your natural pacemaker. It's what sets your base, your resting heart rate. Okay? The electrical signal starts goes this way first and hits your atria. So your atria, so it sends up the signal to your atria. Your atrium contract. Okay, so these contract, and remember these are open. It forces the blood through and into the ventricles. Now these, your atrium and your ventricles, they contract simultaneously. All right, remember. So it's not one atria, then it's not right then left, or left then right. It's both. Atrium at the same time contract, force the blood into the ventricles. The signal is also sent through to your next node. Right. Great. Atrioventricular node, AV node. So your pink cells is your next node. So atrioventricular node is the next node. So it gets the signal from the SA node, and it has a slight delay. I believe the number in your textbook is 0.1 seconds, something like that. A 0.1 second delay. This delay is important. Can someone tell me why the delay is important? So AV node then delays and sends the signal and these are specialized, this is nerve cells in your septum. Remember that this is part of your diagram, right? This is the septum. So it sends these white cells, these are nerves. They're representing nerve cells in your septum and in the walls of your ventricles, in your cardiac muscle. These nerves have a special name. They're called Purkinje fibers. I'll write that on the board. Purkinje fibers. So the SA node sends the signal for the atrium to contract. They contract simultaneously. That signal reaches the AV node. The AV node delays its response and sends it through the Purkinje fibers. Now the timing from when the AV node sends it to the Purkinje fibers is so fast that it allows all of your cardiac muscle in your ventricles to contract at the same time. It's not a chain reaction. It's not contract, 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 contract all the way down. It's boom, it happens fast and the whole thing contracts at the same time. Super fast. Okay, so you have both atrium contract, both ventricles contract. One right after the other. Right? These are your AV valves and your semilunar valves closing. So you have the atrium contract right here, pours the blood into the ventricles contract. When the ventricles contract, it snaps your AV valves closed. Boom, that's your lub, right? When it contracts, it snaps these closed, you hear the lub, it opens your semilunar